Hello everyone. In this video we will discuss about the fifth experiment, that is on the study of lag lead compensator. So here in this figure you are seeing a frequency response of a system. So I am assuming that you know what is frequency response. It is nothing but the variation of gain of the system with frequency and variation of phase of the system with frequency. So this combined figure will be known as frequency response. So here let us say that our system has a frequency response as shown by this dotted curve. So this is our phase curve, and this is our gain curve, and this is our phase curve. So as you can see that the gain is crossing the omega axis at a frequency omega GC. So this will be known as gain crossover frequency. And similarly, somewhere this dotted curve might cross minus 180 degree, and at that frequency we'll say that the phase has crossed over the minus 180 degree line. So that frequency will be known as phase crossover frequency. And sometimes phase does not crosses the minus 180 degree line, that is also okay. So if you look at this dotted curve, you will see that at omega GC phase of the system is phi 2. Phase margin of the system is phi 2. So since the phase margin is positive, we will say that the system is stable. Okay, but being phase margin positive is not enough. Sometimes we want our phase margin to be more, because for a system to be stable, phase margin should be positive, but if it is very low, then at some disturbance phase margin may become negative, and in that case system will become unstable, and we cannot afford to have a system which can become unstable by disturbances. So that's why we keep phase margin much above minus 180 degree, because it improves the relative stability. Now at omega GC phase margin is phi 2. Let us say it is 30 degrees. Now suppose that we want our phase margin to be 50 degrees, and let's call that phi required. So phi required is the phase margin. Suppose it is 50 degrees. So what are the ways in which the phase margin can be improved? So there are two methods. One method is that of lag compensator. So what lag compensator do? It shifts this omega GC point towards left. Okay, how it does that? It drops the gain of the system much quickly. So if you apply lag compensator, what will happen? Instead of dotted curve, we will get this solid curve line. That means this gain will drop quickly as compared to the uncompensated system. So after lag compensation, this should be the curve. Now you can see here, this is omega GC new, and at this frequency, at this new gain crossover frequency, the phase margin is more. Okay, so this is the concept of lag compensator. So this is how it can be done. We know that lag compensator has these frequency responses, or these Bode plots, you can see. So this is the Bode plot of lag compensator. This is the phase gain plot, and this is the phase plot. So you can see that gain is negative. So if you add lag compensator in cascade with this original dotted system, original system with this dotted line. So this much gain will be dropped in this. Okay, so this, if this is 20 log of beta, then K is the attenuation. That means how much the gain is dropped. The gain will be dropped by amount 20 log beta. And here the drop will be small. As you can see that here gain is less negative, here gain is more negative. So here the drop will be small and then the drop will be large. But there is one problem associated with this lag compensator, and that is the angle of the lag compensator is also negative. So it will also, there will also be a drop in angle. Okay, so as you can see here the drop will be more because the phase is more negative here, and here the drop will be small. So as you can see for this dotted curve, when we apply lag compensator, so the phase drops more in this area, and in this area there is some small drop. So what is the procedure of designing a lag compensator? To design a lag compensator, we will see what is phi required. Okay, so let us say phi required is 50 degrees and our phi is 30 degrees. So we will first search in the whole phase plot where we can get 50 degrees. So let us say we can get 50 degrees here. Okay, now instead of 50 degrees we will design for some more. Why? Because after designing, phase also drops. So let us say the requirement is 50 degrees, so we will see 60 degrees. So 60 degree we will search here, and let us say 60 degree comes at this frequency. Now if we can drop our gain by this much amount, so this point will shift towards this zero gain, and when this will shift towards this zero gain, then this will be the new crossover frequency. Okay, and at this new crossover frequency the phase margin will be 60 degrees. Okay, so the procedure is first find where the phase is 60 degrees, and at that frequency find how much drop is needed. So this much drop is needed. So we have to design a lag compensator having this much gain, which can drop this gain by this much amount. So if this is suppose 20 log beta, so 20 log beta will be the gain of the lag compensator. Now another design consideration is that this portion of the lag compensator should be far away from this point. Okay, so this portion should be far away from this point, because at this portion or near this portion this drop in angle comes. So if this portion comes at this point, then their angle drop will be very low, very high, and our phase margin will again become very low, and all of our efforts will go in vain. So the second design consideration is that this part should be much towards left relative to this point. So after designing this lag compensator, you can read more in the manual about these values. What is 20 log beta, what is T1, what is beta T1, what is phi m. So you can do so in your lab manual. So after designing this lag compensator, then the new phase is coming out to be this solid line. Now we designed for 60, but we get a little lower because there is some drop in phase due to the lag compensator. That's why we started with higher phase margin in the first place. So now we will check whether this phase is more than 50 degrees. If it is less than 50 degrees because of the drop here, we go much more towards left, and we repeat the procedure. Now to design a lag compensator, there are two steps. The number one step is to meet the steady state error requirement first. So the steady state error requirement is met first, and then we go for lag compensation. So how we meet the steady state error requirement? So there is a relationship between steady state error and gain Kp. So this gain is the gain of final gain of the system. So for example, our system has a gain K is equal to 10. So our steady state error will become 1 divided by 1 plus 10, right? So this will be around 0.09, so which is nothing but 9%. And now suppose instead of 9% we want system's steady state error to be 5%. So what we will do, we will find out what should be the gain of the system for 5% error by the same formula. So as written here, ESS required is equal to 1 by 1 plus Kp. From here we calculate Kp. So this is equal to 1 divided by 1 plus Kp, where Kp is the desired gain of the system. So Kp is nothing but 1 divided by 5% minus 1. So gain of our system will be 1 divided by 0.05, that is 5%, minus 1. So Kp is coming out to be 19. So 19 is the desired gain for 5% error, and the actual gain of the system is 10. That means we need to multiply some factor to the whole plant, and that factor, let us say that factor is C, or that simply the factor is equal to 19 divided by 10. So if you multiply our system by this factor, our OP loop transfer function with this factor, then the gain of the system will become equal to 19 and steady state error will become 5%. And once we do this, then we will go for lag compensation design. Now to obtain the frequency response of the system, so that we can design lag compensator, we have to do some experiments. Let us say we have a practical system with us, and we do not know much about the system, except we may know how many poles are there for the system, for example, but or what type of system is, but we don't know much about the values of these poles, for example. Now if we are giving some input RS and we are getting some output CS, so let us say we are giving a sinusoidal input to this system, shown by this red color, having frequency omega 1, and correspondingly we are getting this output which is having 2 magnitude, and the phase shift of the output with respect to input is 30 degrees. So we will say that the system has a gain of 2 and a phase of 30 degrees at frequency omega is equal to omega 1, right? So gain of the system is nothing but magnitude of output divided by magnitude of input. Similarly, we now increase the frequency of the input, let us say to omega 2, and we will do the same procedure again. We will check the gain of the system, so it will be now 1.4 and the phase of the system will be 10 degrees. Now at omega is equal to omega 3, we are getting a gain of 0.5 and the phase is 0 degrees. So we keep on doing this, we keep on increasing the frequency of the input, and correspondingly we are checking the gain of the system and phase of the system, and then we plot that with respect to omega, where omega is the input frequency. So this is how we get the frequency response. So this is one of the method of finding out the frequency response. There is one more method that we will be using in our system, and that is the use of Lesage's figures. So we find out the Bode plot of the plant by this another method, in which in the CRO we move to XY mode, and on x-axis we give the input, which we are taking sinusoidal input with varying frequency, and at the output we are just at the y-axis we are taking the output of the plant. So by taking this we will get this type of figure. We have to here measure some points, and based on these points we will get the Bode plot or frequency response of the system. So these points are A, B, where A is the maximum value of X in the figure. So this is the maximum value of X. Similarly, this is maximum value of Y in the figure. And then we are getting X0, which is the intercept or you can say the figure is crossing the x-axis at this point. This is X0, and figure is crossing y-axis at this point, that is Y0. And the slope also, because sometimes this slope is positive and sometimes this figure is tilted towards left instead of right, so the slope will be in the second quadrant. So we will record these things for varying frequency. Okay, so for different input frequencies we will get different shapes, as we will see shortly, and for that we will record A, B, X0, Y0 values, and from here we will find out magnitude and phase for the frequency response. So this is one example of finding out the Bode plot with the help of XY plots. So we do not have practical system with us, so we are simulating that in MATLAB, and this is one of the example how to do that. So let us say we have our system with numerator matrix 10 and denominator matrix 4, 3, 1. So this we have discussed in detail, what are these numerator and denominator matrices in our previous experiments. So according to this, our transfer function will be 10 divided by 4s square plus 3s plus 1, and numerator matrix is nothing but the coefficients of the numerator of transfer function, and denominator matrix is the matrix with coefficients of the denominator of the transfer function, that is 4, 3, 1. So let us start with this transfer function. Let us say our system is like this. In practical system we do not know about these values. Okay, so we will just give some input and record its output. Now in pole placement also we have done these steps, so this will be easy for you to understand. First we define a transfer function Trn with numerator and denominator. Then we convert this transfer function to steady state to get A, B, C, D matrices. Then we form a system sys with this A, B, C, D matrices. So this sys will be formed to plot the output. So you already know about this. The output of the system can be plotted using LSIM command, like we did in pole placement. Now in figure 1 we are drawing the Bode plot of this TRN transfer function, just to see how the transfer function looks like. And then here we are plotting the output of the system with respect to some input. So now what is that input? So this is the system, this is input Q, this is the time duration for which we want to plot, and these are some initial conditions which we must take. So we are starting with initial conditions x0 0 0. So there are two initial conditions because this is a 2-order system. Now time we are taking from 0 to 20 pi. So just a random selection. So we are taking time from 0 to 20 pi with a step of 0.01 in between. So the time goes like this: 0, 0.01, 0.02, 0.03 up to 20 pi. Then we are starting with some input frequency, omega 1 is equal to 0.15. Now input is 1 magnitude into sine omega t, where omega is the frequency, t is this time period. Okay, so now we are in figure 2. We want to plot the output. So y is equal to LSIM command used for system sys, and input u, time t, and x0 as the initial conditions. Now this is something which we are skipping right now. This is we are just taking time after 20 seconds because this time is varying from 0 to 20 pi. So this means 0 to around 62 or 63 seconds. So when we plotted this, we saw that our initial cycles of time were not coming out to be sinusoidal because there were transients initially, and then the system goes to steady state. So we took time greater than 20 seconds after which the system was in steady state, so that we can analyze better. So this part you can skip. Just consider that the final output of our system is y1 and the input which we are giving is u1. Now we are plotting it. We are plotting output with respect to time, and on the same plot we are plotting input with respect to time, so that we can compare the two. And in the third figure we are plotting XY plot, because on x-axis we are taking input and on y-axis we are taking output. So now we will run this program and we will see what is happening for a better picture. So these are the figures which we are getting. This is the XY plot. This is the input versus output. So input with time and output with time on the same graph. So as you can see, this is the input having unity magnitude, and correspondingly we are getting this output having magnitude near to 10. And the phase difference is this much. Here the input signal crosses the x-axis or time axis. Here the output signal crosses the time axis. So there is some phase difference between output and input. Now this is the XY plot which is of interest to us, because we have to find out some points on this plot. Right now we are taking omega as 0.15. If we change omega, this plot will also change, so the points on it will also change. So this is the B point, that is the maximum value of y, which is coming out to be 9.85. This is the A point, the maximum value of x. So x is coming out to be near 1, so let's consider it 1, 0.996. Now the plot is crossing the y-axis at this point. So this is your y0, which is 0.000278. Sorry, it is not y0. Y0 is 4.369. So x is near 0. That means we are on the y-axis, and y is coming out to be 4.369. So this is y0, 4.369, and x0 is coming out to be 0.442. Right, so now we will draw this table. So this table was drawn earlier when we took input magnitude to be 2. Now we are taking input magnitude to be 1, so our table will be different. So what we will record? We will record the frequency value of A on the plot, B, x0 and y0, and then we will increase the frequency and do that again. So now increase the frequency to 0.25 and run the plot. Run the program to get the plots. So this is the XY plot. As you can see, the figure which contains input and output has changed a little. The output has gone down from near 10 to around 9.5, and this is the input. The phase is increased. If you compare from the previous case, the phase is increased by increasing the frequency of the input. Similarly, this point, this plot has also changed, and if we look at the points, so now B is 9.428, X will remain near 1, this is A is 1, then X0 will be this point which is increased, 0.7076, and y0 will be this point which is also increased, this is 6.665. so in the similar way we will keep on increasing the frequencies like this, and we will keep on recording A, B, x0, y0 points, and once we get this we can plot the Bode plot of the system. Okay, so now we will run this program. So this program is for lag compensation. Here we have assumed that we had a practical system for which we have find out A, B, x0 and y0 values for different range of frequencies. Now we get A, B, x0, y0 values, so we will find out the frequency response of the system, and we will find out this type of response of the system, and from this response we will try to find out this Ka, okay, that is 20 log beta, and then we will try to find out this T1 and beta T1. So beta is the same beta here, so this will come from here, and we will find out T1. So T1 is the corner frequency, 1 by T1 is the corner frequency of lag compensator, and like we discussed earlier that this part of the compensator should be well away from the from this point, that is the point of new gain crossover frequency. For this what we do, we keep 1 by T1 1/10 of the omega GC new frequency. So if omega GC new is for example 5, so we will take 1 by T1 as 0.5. In this way we will ensure that this part of the lag compensator remains more towards left as compared to this point. So since we get the response, we need to find out these these values. So the good way is to convert this accurate frequency response to approximate Bode plot. Okay, so if we can approximate this curve, the Bode plot of this, if we can approximate, then we will be able to find out the corner frequencies of this curve, and what is the gain of this curve, what are the corner frequencies of this curve. So if we can do this, then we can find we can write the transfer function of this. Okay, so we had a practical plant, from there we have obtained this frequency response, but we know nothing about the values of this response. So what we are doing is we are approximating this frequency response as Bode plot, and then we are finding out the transfer function of this practical system. So we'll do this approximation, and then we'll move forward to design this lag compensator. So let's run this program. So in this program there are two steps. One step is to find out the steady state error, as we have discussed earlier. So I'm running this program. So it is saying save the figure and enter value of k from the gain of frequency response curve. Okay, so in this program we have written all these values of omega, a, b, x0, y0 and slope which we obtained here. And once we do this, we run this, and it is plotting a frequency response by first finding out gain and phase. So gain has this formula. We can find out gain like this, b by a, and phase has this formula. Okay, so this you can see in your lab manual also. So this is the formula for gain. In decibels it will be 20 log of this. This is the gain without decibels. So the gain in decibels will be like this. Phase will be like this, minus of sine inverse x0 by a, or minus of sine inverse y0 by b. Now if this slope is like this, okay, so if the slope is negative like this, then the formula for gain remains the same, but the formula for the phase changes. So just 180 degree is added here, 180 degree minus sine inverse of x0 by a. So for this we have defined another matrix of slope, where 1 means positive slopes and 2 means negative slopes. So just by looking at the xy plot, we can decide whether the slope is positive or negative. So if slope is 1, then this formula is used, and if slope is 2, then this formula is used to find out phase of the system. So it has plotted frequency versus gain and frequency versus phase. That means the frequency response of the system. So this is the frequency response of the system which we are getting, and from this the program says that save the figure and enter value of k from the frequency response curve. So if the system is type 0 system, then our Bode plot starts with a slope 0. So this you must have learned in your third year, that when we draw Bode plot of type 0 system, type 0 system means a system which does not has a term of 1 by s, that is integrator is not there, or type 2 system will be 1 by s square, and type 1 system will be 1 by s, and type 0 system means there is no 1 by s term. So in our system here, this is 10 divided by 4s square plus 3s plus 1. That means there is no such term like this 1 by s here. So this type 0 system. So for type 0 system, the slope starts with 0, and then when first corner frequency will at one corner frequency, there will be a slope of minus 20 dB per decade, and then at another corner frequency there will be further slope of minus 40 dB per decade. So at each corner frequency the slope drops down by minus 20 dB per decade. So our system has two poles. This was the example. So our system is also a similar kind of system having two poles. You can see from the denominator. And so since the system has two poles, there should be two corner frequency. So we are assuming that although we do not know about the system values, we do not know whether these are the values or not, because our plant is a practical one, but we are having some information about the type of the system, that is, it is type 0 system, and maybe it has two poles. So let's enter the value of gain. So here gain will be 20. So when we draw Bode plot, you must remember that for type 0 system the gains start at this the Bode plot start with the gain, that is, the line starts from 20. So the gain here is 20. So I am writing down 20 here. Now it is saying that at enter and so this part is wrong here. KdB is 20 only. The KdB is not 20 log 10k, it is 20. So now enter first corner frequency from the graph in hertz. So how you will find out first corner frequency? So you know that our plant has two poles, so we will try to find out first corner frequency. First we will draw two lines, one of minus 20 dB per decade and one of 40 dB, minus 40 dB per decade. So if you look, this is 20 and this is 0, right? So if we start from 20 at omega equal to 10, so by the time the line reaches 100, there should be a drop of 20. Okay, so if we start from here and go up to here, so I have crossed one decade on x-axis, so I am seeing that there is a drop of 20 dBs. So this line is having slope of minus 20 dB per decade. Similarly, if I draw another line of minus 40 dB per decade slope, so it will start from 20 and by the time it reaches 100 it should drop by 40 dBs, so it will go to minus 20. So this is minus 20, this is 20, so in a decade it has dropped to 40 dB. Now as per the transfer function, this part should be 40 dB, minus 40 dB per decade after the second corner frequency. So I am just extending this. You will know what I am doing very soon. So this is minus 40 dB per decade line, and then just take this and try to fit this line somewhere here, because we are approximating the frequency response for Bode plot. So it is around here. So the plot starts with 20 and then it encounters the first corner frequency. So there is a drop of minus 20 dB per decade, and then it encounters another corner frequency. So there is further drop of minus 20 dB per decade. So this is our Bode plot. So the first corner frequency, as we can see from here, is around 0.2728. Okay, and second corner frequency is around here. So this should be, if this is 1, this is 0.85, that means there is gap of 0.03, so 0.09, so it will be around 0.94. okay, so 0.28 and 0.94. so enter the first corner frequency, so it will be 0.28. and the second corner frequency 0.94. So since we have given all the values to the program, so the approximate transfer function is this, formed by corner frequencies and gain. So this is k divided by t1s plus 1 into t2s plus 1. Now as we have find out the transfer function of our practical system, things will become very easy for us. We can start a control system designer, which is in MATLAB, based on the transfer function. Which transfer function? Based on this calculated transfer function. So a control system designer is opened. So now let's read what it says. It says save the body plot figure, calculate phase margin and gain crossover frequency from the curve, and then right click on the time response plot, click characteristics, and then click peak response, settling time, rise time, steady state. Take the snapshot of the figure and save. Okay, so we have this figure. We are getting the gain margin, phase margin. So our phase margin is coming out to be 30.5 degrees, which is very low. Then this is our time response, and this is our root locus. So I am seeing all the characteristics: peak response, settling time, rise time, and steady state. So if I go to steady state, so it is showing a value of 0.952. That means there is a steady state error of 0.047 something. So that means 4.7% error, the steady state error. So now let's take snapshot and save it somewhere. So I am saving it here. So this was saved earlier. Okay. Now first step is to find out the gain for which steady state error becomes equal to our desired value. So right now the steady state error is 4.76. Now suppose that we want our steady state error to be 3% only. Okay, so by this formula we can find out what should be our gain. Okay, so right now we have gain of 20, as you have seen. So for that steady state error is coming out to be this. But if we want some other steady state error, so we will get the corresponding gain. So let's say we need only 3% error. So I am writing 0.03 here. So as you can see from here, so for 3% error with this formula we can find out KP. KP should be 32, but our gain is 20. That means a further gain of 32.333 divided by 20 is required in the system. So the required gain in the system is 1.6167. That means additional to 20. So if you multiply this gain by this, so we'll get 32.33. So how you will do this? For this we have to go for control system designer again. So here we have very wide number of options. We can find out various transfer functions. So the transfer function which we are interested in is R2Y. So double click this. So this is our transfer function. We can vary G, we can vary H, C, or F. G is nothing but our transfer function, the open loop transfer function, and C is the gain here. So we want to vary this gain. So this G has 20 gain, and this gain should be 1.6, so that the whole system gain becomes equal to 32. So this we are going to do. We are changing the open loop system gain. So double clicking on C, we can put C as 1.617. I think this was the value, 6167. Okay, So by doing so, our steady state error should be 3 only. Okay, so let's see. So the final value is 0.97, so that means our steady state error is 3%. But there is problem with this. What happens when we change gain? So when we change gain, we can see that we have increased the gain, right? So increasing the gain means this has shifted towards right. So initially it was omega gc dash, and when we increase the gain, we move to omega gc. So at omega gc, phase margin is further low, so phase margin reduces, which we do not want. So phase margin has gone to 24. Now we will design our lag compensator to compensate phase margin. So initially it was around 30, now it has become 24, and let's say we want our phase margin to be 50 degrees, or let's say 60 degrees. So now we have to find out the attenuation required. So from where we will find out attenuation required? So we will again look at this figure. So if we are getting 24 degrees here, because this is our gain crossover frequency, now we will move in this curve to find out where is 60, where is the 60 phase margin, and at that phase margin we will find out omega gc nu. That means and what attenuation is required. That means if our gain reduces from here to 0, then this will be our new gain crossover frequency, and at this frequency we will get 60 degree phase margin. So we need Ka and omega gc nu. These two values we need to find out. So for our system, let's find out 60 degree phase margin. So I am adding grid here, and then I am finding out the location where we will get 60 degree phase margin. So I am going to Bode editor here, right, and then I am taking this zoom in option, and 60 degree phase margin will be at minus 120, because 180 plus 60 is 60 degree phase margin. So it will be somewhere here. So I am zooming in this region. So as you can see, 20 is here. So this point we should note. What is this point? So I am zooming in further. So this point is around 6.16, and at 6.16 our gain is around 15.7. So the two things we have to note: 16.16 and 6.16 and 15.7. Six 6.16 is omega gc nu, and attenuation Ka is 15.7. Now if this 15.7 drops to 0, then okay, so we are writing it here. Enter the attenuation required. So attenuation required is 15.7, right? Because at 60 degree phase margin we have seen that this is 6 point something, and the attenuation required, that is this much, is 15.7. so if this point goes to here, then this will be our new gain crossover frequency, and our phase margin will be 60 degree. Now enter new gain crossover frequency. So it was 6 point, let me check, 16. Now the program has done its part. So this is our lag compensator gain. So from here it has calculated beta, because Ka or 15.7 is equal to 20 log beta. So from here we found beta, and this is our new gain crossover frequency, 1/10 of new gain crossover frequency as discussed. So our gain crossover frequency was 6.16. So 1/10 of this will be 0.616, and 1 by t will be 0.2584, and similarly beta, you can calculate 1 by beta t. Now there is one important thing, that our system is having electrical parameters. So because the system is composed of R, C and L, system can be in another domain also, but the system we are considering is in electrical domain. So in electrical domain we can design lag compensator like this. R here, there is one resistance R, there is a resistance here R2, and one capacitance. So if we find out its transfer function, will give this Bode plot. Okay, so you can see this in theory or in lab manual, but this is our lag compensator. So now we know that what is beta and what is t. Now we know that there is a relationship between R, C and R1, C and R2. How you can find? You can find the transfer function of this, and you can compare that transfer function with the formula for transfer function of lag compensator. Then you will know that these are the formula. So this is beta, this is t. You can design your compensator by choosing values of R1, R2 and C, so that this expression is correct. Okay, so this is the complete here we complete the design of lag compensator. We just find out R1, R2 and C, so that we get the beta and T like this. Now just for the completion purpose, I have also drawn the Bode plot of the uncompensated system and that of the compensated system. So you can see the Bode plot of compensated system has lower new gain crossover frequency than the Bode plot of uncompensated system. So in uncompensated system, the phase margin is low here, and when we go for compensated system, then we will read phase margin from here, because this is the new gain crossover frequency, and here the phase margin is more. So in this way the phase margin of the system can be improved by adding a lag compensator. Although there is a drop in phase also, that will because of lag compensator, that will reduce the phase margin, but the net result is overall increase in the phase margin of the system.